Okay, I think we're on. Do you want to talk to make sure the YouTube is actually catching up to us?
Sure, we can attempt that.
Oh, no, you don't have to share screen quite yet.
Whatever. It's okay.
Okay, yep, I'm seeing it, so it looks like we're all good. And it is 11 o'clock, so let's get started. Hello, welcome back to the Philip J. Currie Dinosaur Museum Virtual Speaker Series, where we have paleontology and science guests call in for presentations about whatever they want to talk about. Today we have Taia Wyenberg-Henzler, who is a PhD student at the University of Alberta in Corwin Sullivan's lab. She's studying the bite trace or feeding traces of tyrannosaurs and their jaw structures and how their jaw structure influences feeding traces. Taia has been interested in dinosaurs well before that, according to her, ever since she was 2. I don't know how she remembers that long ago. But taking that love of dinosaurs into study, she did a Bachelor of Science in Geology at Mount Royal University in Calgary. And after graduating in 2018, she took her studies to Carleton University in Ottawa, where she studied the ecological interactions and implications of herbivorous dinosaurs, specifically hadrosaurs and ceratopsids. And today's presentation is part of her master's thesis on the feeding behaviors of juvenile herbivorous dinosaurs. And I think with that, Taia, you want to start talking?
Sure thing. So like Jackson mentioned, this will be on my MSc research. So I guess without further ado, let's get started. First of all, let's start off with some context. During the Late Cretaceous, we had this giant interior seaway running through North America, which started all the way at the beginning in Alaska, and it's extended down through to Texas. And we also had a bunch of mountain building at this time, which was responsible for the formation of the Rocky Mountains and the addition of British Columbia to our continent. And this mountain building was a source of eastward flowing rivers, which contributed to the overall boggy environments of the time. So this is what Late Cretaceous North America would have looked like. And it was home to not only a wide array of different dinosaur species, but also a lot of dinosaurs in terms of the number of individuals per species. So some of the herbivores that we would have seen, especially in our more species-rich assemblages, were ankylosaurs, so things like notosaurids and the club-tailed ankylosaurids. We also had up to 2 different types or main groups of ceratopsids, so our horned dinosaurs, so our centrosaurines, which include our Pachyrhinosaurus, and our chasmosaurines, which include things like Triceratops. We also have 2 main groups of hadrosaurs, so our crested lambeosaurines, things like Parasaurolophus, and then our not so crested hadrosaurines, so things like Edmontosaurus. And of course, at this time, we would have had juvenile versions of these different dinosaur groups running around, but we also had smaller herbivores running around, so things like our dome-headed Pachycephalosaurids. So there has been some research done investigating how so many herbivores on the scale of what we see today in Africa coexisting on a landmass that's actually about half the size that the African continent is. So a lot of dinosaurs in a really, really small space comparatively to what we see for mammals today. And there's a lot of questions surrounding this, such as, how could we have had so many dinosaurs in one spot? How was it even physically possible for them to have coexisted? And some of this research has focused on adult megaherbivores, so the really large dinosaur species. And this research has suggested that there was resource splitting that facilitated this coexistence. However, this doesn't really tell us much about what's going on with smaller body sizes. So what were the young of the large herbivores eating, for instance, which is the first half of this presentation. And then What about the adults, small herbivores? Were they eating the same things? Were they eating something different? That was also another big gap in our understanding of what was going on at this time. And that's the second half of this presentation. So some of you might be wondering, wouldn't juveniles eat the same stuff as the adults? And the answer is not necessarily. Why not? Because of this thing called an ontogenetic niche shift. What is an ontogenetic niche shift, you might ask? Well, when we look at modern animals living today, they often change their diet as they grow, either because of sheer changes in overall body size or changes in overall size as well as shape as they grow. And when individuals of different growth stages eat different things, we give it this fancy term called a dietary ontogenetic niche shift, or an ONS for short. So what do we see in modern animals when ONSs occur? Well, if we see large changes in size during growth, such as in alligators, for instance, there's an increase, for instance, in prey size. So this boils down to the idea that the bigger you are, the bigger the things you can eat. But in alligators, we also see changes in size accompanied by disproportionate changes in shape as well. This is not necessarily a requirement for a dietary change with growth to occur, but if it does occur, it makes it a lot more likely. So in the example of our alligator again, we see a change in the relative length of the snout compared to the rest of the skull. So as the alligator gets bigger, its snout becomes a lot longer relative to the overall length of the skull, even though the skull is also growing in shape. It's just that the snout grows a lot faster. So this is where we start to get into some of the fancy terminology. There's basically two ways that an animal can grow. There's a way it can grow proportionately, which is termed isometry, but that's really just a fancy way of saying that there are changes in size and only in size as the animal grows. So you can think of it like our smiley face here, where everything just becomes bigger and bigger and bigger, but nothing really changes in terms of the relative size of things as everything gets bigger. It's just scaled up. Now, the other kind that we can get is this disproportionate growth that I mentioned earlier, which is the fancy term for it is called allometry. Now, allometry is referring to changes in size and shape. And there are two subcategories of this. You can get a disproportionate decrease, so negative allometry, where the overall size of the animal grows a lot faster relative to a part of the animal. So for instance, the eye size changes relatively slower compared to the overall skull size. You see this in humans as well, where the eyes don't really change much overall to the overall size of the individual. You can also get a disproportionate increase or positive allometry, where a feature grows a lot faster compared to the overall size of the animal. And that's getting back to our snout example. The way we determine this disproportionate versus proportionate growth is mathematically. And you might recognize this equation from high school mathematics. It's RY equals MX plus B. You don't really need to know that, but I thought I'd bring that up because it is something that we use quite a bit when we're assessing these changes in size and shape during growth. Now, what about in dinosaurs? Do we have any previous examples of these dietary shifts or ontogenetic niche shifts in dinosaurs? And the answer is we have some pretty good examples. One such example is Limosaurus, which is a theropod. So in Limosaurus, we see a loss of teeth with growth. And this has been used to propose a possible dietary change with growth, where the smaller juvenile forms, which actually have teeth, are thought to have been omnivorous, eating a mix of plant and animal material. And then as they grow, they lose the teeth and become potentially more herbivorous, so more plant eating, until they become adults and they have absolutely no teeth in the jaw. Perhaps the most famous individual or group that is likely to have shown an ontogenetic shift is T-Rex. And we see quite a few different changes in the overall skull shape. As a point of interest, actually, juvenile T-Rex was originally thought to have been a different species altogether because of how much the skull and overall morphology changed with growth. But now we know that that is actually not the case, and they're the same species. So what do we see? Well, we see an increase in skull robusticity. Basically, the skull becomes beefier or chunkier as the animal grows. We also see a decrease in snout length. So the animal's skull basically becomes a bit more squashed in and a bit more like pug-like, which has some biomechanical implications as well. We also see changes in the shape of the teeth, where juveniles tend to have more blade-like teeth, and then the adults become more cone-like. Another tidbit of interesting information is that we see this change in tooth morphology in alligators as well. So all these features changing during growth combined suggests that perhaps there was a change in prey size and bite force, where juveniles were preferring maybe more smaller prey and didn't really have the great big bite force necessary to process bone. So basically, we're going from something like an ankle biter to a bone cruncher, to put it in punchier terms. We also see it in our herbivorous dinosaurs as well, such as our sauropods, like Diplodocus. So there are also a number of features that suggest that there was a dietary change with growth in this group. We see changes in the snout shape and the length of the snout. So the snout actually becomes longer, again, like in our alligator example. And we also see a change in the number and the distribution of the teeth. So in the juveniles, we see teeth all the way along the maxilla and the premaxilla, but in the adults, it's restricted to the premaxilla. And these together have been used to suggest that there were changes in plant preference with growth. Basically, the juveniles are thought to have been plucking at a little bit of everything, using their different types of teeth to do this. And the adults basically just mowing down coarse vegetation near the ground, kind of like a big vacuum cleaner, if you want to think about it like that. Now, bringing back to our Late Cretaceous example in North America, are Ceratopsids. So as I mentioned earlier, we've got our two main groups, our centrosaurians and our chasmosaurians. And what we know, and we have it well documented, that there are changes to the frill and horns with growth in our ceratopsid group. So things like Triceratops or Pachyrhinosaurus. But we're not entirely sure what's going on as far as the diet is concerned. However, we do see a significant change in size with growth. So this image here on the side is an example of Triceratops in a growth series, and all the skulls are actually scaled to the same exact size. So there's quite a big difference. You go from something about the size of a cat to larger than an elephant over the course of several years. So this significant change in growth suggests that dietary changes are likely, but we still don't know what they look like. And then our other group are hadrosaurids, which include things like our Edmontosaurus and our Parasaurolophus. Also have well-documented examples where we see changes to the cranial crest. Once again, these skulls are scaled to the same absolute size to one another. And on the left-hand side of your screen, you'll see a hatchling-sized Hypacrosaurus, and then on the right side, we have a fully grown adult. So once again, we don't know if there are dietary changes, but there seems to be quite a big difference in size. A very big difference, in fact. Here's an image that depicts a freshly hatched Edmontosaurus compared to a human, and a fully grown Edmontosaurus compared to a human. So we're going from something that was less than 5 kilograms to something over 5 tons over the course of a few years. So this means that dietary changes, again, were likely just based on sheer changes in size. But again, we don't know what these dietary changes would have looked like, which is what the first half of this presentation is aimed to get at. So how exactly do you go about doing this? Well, one way to do it is to look at various different parts of the skull and take a bunch of different measurements that are reflective of dietary differences between modern groups. So one really good example is between our ungulates, where we see changes in like facial proportions, and that's just that they're doing different things as far as diet's concerned. And so we can use these same measurements in our extinct dinosaurs and see how they change with growth or with size. You can also look at things like snout shape, where a narrower snout shape is more indicative of an animal that might be more selective in its feeding style, so a plucker. And then a wider snout is inferred to suggest an animal that's less selective in its feeding style. So it's more like a lawnmower, where it's on a seafood diet, if you will. It sees anything and it eats everything. So let's get into the result portion of this graph and these results here. Just to orient you, we've got our snout shape on the y-axis, where we have our narrower plucker style morphologies on one end, and then our wider, more style morphologies on the other end. And then on our x-axis, we've got a change in size, where the smaller individuals or the smaller x-axis values and our larger individuals are on our right-hand side with the larger x-axis values. So in our hadrosaurs, what we see is a lot of overlap between snout shape, between our various groups. And the only place where we see a lack of overlap between our groups and our individuals are at the two extremes, our really, really large individuals and our really, really small individuals. Now, this is unlikely to have indicated a difference in overall snout size as far as diet's concerned, and more likely a reflection of our sampling complications. So when you go to something that's really, really small, it's really hard to find good examples of these really small individuals because they don't stand the test of time. They're very unlikely to be found and preserved in the fossil records. So if we had all those individuals, it's likely that we wouldn't be seeing this gap at the smaller end. Now, what about at our larger end? What is the reason for that lack of overlap? Well, it's likely because of the inclusion of the really large hadrosaurians, or Edmontosaurus specifically, which were the biggest hadrosaurs that ever existed in North America. So these guys just separate out because they got so much bigger than everything else. And so it's not really a change in ecological role or their role in the ecosystem as much as just a difference in size. Now, what about in our ceratopsids, our horned dinosaurs? Well, we see a very similar pattern where there's not a whole lot of difference in the distribution along our y-axis or our snout shape axis. But again, we do see a lack of overlap between our two groups at the two extremes. Again, corresponding to our sampling error or our lack of sampling at the smaller body sizes because of preservation issues, and then our inclusion of a really big group of dinosaurs, specifically Triceratops, which got really, really big. And so not so much an ecological or community role difference, but just a size difference. So in summary, we don't really see a size and snout shape, but we do see an absolute difference in size that probably would have made juveniles more selective, so a little bit more like our plucker style group than their adult counterparts. So what else can we figure out based on those skull measurements that we took? Well, there are a few that I want to go over. This is not by any means the complete picture, but here are some of the more interesting ones, particularly to do with feeding reach. So this is the red lines indicate the relative dimensions of these measurements compared to overall skull length. So in our juvenile dinosaurs, we see relatively shorter snouts, which is similar to our browsing examples that we see today, such as our giraffes. And then as they grow, we see a progressive lengthening of the snout, which is similar to more of our grazing type examples that we have today, such as our horses. So what happens when you change the length of the snout like this? Well, it means that we get an increase in overall feeding range. So as they get bigger, they can reach more food at different heights. And we see a decrease in the relative bite force at the snout tip. And that's just because the muscles that connect to the back of the jaw are responsible for providing all of the forces that are associated with the bite. And so the longer your face gets, the farther away you are from those muscles. And so the bite at that snout tip becomes decreased. Now, we also see a change in the depression of the snout below where the teeth end as the animals grow. So in juveniles, the snout's less depressed. So the cropping mechanism, the cropping tip at the very front of the face is a lot more in line with where the teeth would have ended. And then as the animal grows, the snout becomes more depressed or extended below that tooth termination point. And this increase would have resulted in an increase in the relative bite force at the snout tip. So the opposite of what we just saw for our snout lengthening scenario. So we've got a bit of a mixed signal here. Now, in our ceratopsids specifically, we see a change in two other variables that is particularly interesting. Namely our coronoid process apex distance. So that's on the lower jaw, and that's one of the main areas where the muscles are attaching to. And so when you change this distance, you get a change in the amount of leverage because the lower jaw of all vertebrates, including us, changes, can be modeled like a third class lever, for those of you who are familiar with that concept. Basically, this boils down to an increase in the relative bite force. So as the animals grew, they actually became they had a lot more force behind their bite. Now, if we look at the quadrate breadth, so the back of the skull, the distance between the two jaws on the left and right sides, we see a decrease in the relative resistance to torsion and an increase to muscle attachment area. So you can actually test this out yourself. If you take your two hands and you place them on the sides of your jaw and you move them up and down, you can actually feel these muscles at work. And so when I'm talking about torsion here, I'm actually talking about something called wobble resistance. Basically, the changes in the width of your skull means you get a change in your resistance to this amount of wobble as you grow. And when we interpret this together, it actually means we have a decrease in the relative bite force. So again, we get another mixed signal where we have some values that are suggesting that we get relatively increasing bite forces and then decreases in bite forces. So we also see a change in the cervical musculature, the neck musculature in our hadrosaurids, which is in itself particularly interesting. So the paroccipital processes are some of the more important areas of attachment for the neck muscles, and these are responsible for lifting the head and moving the head around. So in juveniles, what we see is a relatively wider paroccipital process breadth. So it's negatively allometric, and it becomes relatively more narrow as the animal grows. And this means that we have a decrease in the attachment area for these neck muscles. So this suggests that these neck muscles were actually less important as the animal grew, at least in terms of feeding behavior. Now, what does this mean in terms of how the animal is actually eating and behaving? Well, we can draw some parallels between our modern animals, where our juveniles with their wider paraccipital processes may have fed a bit more like our giraffe here, using head motions to pluck vegetation off of branches, whereas the adults would have relied more on their bite forces to crop vegetation. So they would have been more bitey, like our cow here. We also see this pattern in our ceratopsids. However, it's actually the opposite to what we just saw in our hadrosaurs. Now, as I mentioned before, our narrow paraccipital process breadth is in our juveniles, and as it becomes wider, it increases our attachment area, right? And so that might suggest that our juveniles were instead our biters, and then our adults were pluckers. However, ceratopsids are a bit weird because they also have a lot of this head ornamentation. They've got these great big frills that are made of bone, and a lot of these like horns and all kinds of other crazy head ornaments. So it's possible that this change in neck musculature is instead a reflection of how heavy the head is and how easy or hard it is to lift. So instead, the signal that we're picking up in our ceratopsids might be more of a reflection of increasing head weight as opposed to changes in feeding behavior. So what does this mean in terms of the big picture? What were we seeing, and how can we interpret what's going on in terms of our juveniles versus our adults? So juvenile megaherbivores seem to have been more selectively feeding on our softer head vegetation, so stuff that didn't require so much chewing or bite force as much, because they were still just babies figuring out how to eat, much like we have to figure out when we're learning how to eat solid foods. And then the adults were able to be less selective in their feeding style. They're a bit more like lawnmowers, and they fed on vegetation growing at a variety of heights. So something like this, where we see a change in diet with growth, and perhaps even the adults feeding higher up in the canopy and the juveniles feeding a little bit lower on the softer, mushier foods. Now, what does this mean in terms of our big picture question? What about the rest of the dinosaurs in this community? Did the smaller adult herbivores eat the same thing as the baby dinosaurs? Was there competition? Or put another way, did young dinosaurs share resources with these smaller dinosaurs, or were they really bad at sharing? And when we look at the size and types of dinosaurs that we get in these communities, it's just that these young dinosaurs were not fantastic sharers. So to explain this more fully, we got to take a step back for a minute and look at what we see in modern ecosystems. So for example, on the Serengeti, we see representatives of all body sizes, even when we include the juveniles. We have a pretty full body size distribution here. Now, if we look at our dinosaur ecosystems, we have this huge gap at about the middle size spectrum. We have lots of little things and we have some big things, but we don't have anything really between the middle. And why is this? So some researchers have suggested that it's because of differences in the juvenile to adult body size of our largest animals, and differences in life history. So mammals like us and lions have a lot larger babies compared to the adult body size. And they also nurse their young, whereas dinosaurs did not. Their young started off very small. They hatched from eggs no bigger than a football, and then they had to grow into multi-ton behemoths. So in our mammals, we don't get really a whole lot of a change in diet with growth, but in our adults, in our dinosaurs, we do see a dramatic change in diet with growth. And so these differences in life history may have influenced these community interactions, where we have the young of these larger species occupying multiple roles throughout the community in different stages of their life and interacting with different groups. So this gap is not necessarily a gap, but it's filled by the teenagers of the large-bodied groups. And so because we know our hadrosaurs and our ceratopsids underwent these dietary changes with growth, we suggest that there is something similar going on in our herbivorous communities. But up until my master's research, nobody had really looked into that from an ecological perspective or a community role perspective. So questioning really comes down to share or not to share. And the way you can investigate whether or not there was this sharing or not going on is to produce a graphical picture of what types of plants these baby megaherbivores and small adult herbivores were eating using these cranial measurements that I mentioned near the beginning of this talk. So there are two possible scenarios. The first one is this ancestral competition scenario. Basically, the ancestors of these individuals had to share it first. They show quite a bit of overlap with one another. And then as time goes on, they change their roles occupied in the community. And so when we start to look at the late Cretaceous forms, they're actually quite separated in this graphical picture space. And so you have these ancestors plotting more in the middle between the more derived or late Cretaceous groups, essentially. Now, the other possibility is that we still have competition in late Cretaceous. So these groups still had to share, even after they had been living on the same landmass with each other for many millions of years. So getting into what we are actually seeing when we plot these measurements out into these graphical picture spaces. With our examples here on the side, just to give you a point of reference, when we plot our basal or ancestral forms in the space, we see that they plot pretty close to one another. But then when we take our more derived forms, our late Cretaceous forms, we see that there is quite a bit more separation with one another. So we see something similar to our top diagram here, where we would expect to see ancestral competition and then later divergence in community roles as a consequence of that. However, we also see that there's some overlap, particularly between our young megaherbivores, our ceratopsids and hadrosaurids, and our leptoceratopsids over on the side of PC1 here. And it looks a lot more like this bottom diagram where we have quite a bit of overlap. So it seems like we have a mixture of both scenarios going on. Now, whether or not that definitively suggests that we have competition going on between these three groups or not is still something that needs to be looked into, because these skill variables don't account for things such as differences in daily activities, for instance. So there could be variables that these guys are splitting the resources along that we haven't accounted for yet. But another interesting question that arises from this potential for competition is how well did the young dinosaurs share with the smaller dinosaurs? Were they good at sharing, or were they not so good at sharing? Well, we can also look at the relative amounts of food consumed by each group per given area, which is just really a complicated way of saying how much of the resource pie did each group get and how big was that slice. And you can do this by constructing something called a browse profile, which showed these pie slices in terms of feeding heights. So how high in the canopy different dinosaurs were feeding at. So to construct these browse profiles, what you can do is you can take a model ecosystem. In this case, we're going to take the really well-sampled species-rich Dinosaur Park Formation from southern Alberta. And we're going to take some information from previous studies about body size, growth rates, population size, metabolic rates, and feeding heights and all this, and feed it in there as well for each of these groups. And what you get at the end of it is something that looks like this. Now, the question becomes, how do you really interpret this? Well, if you look at it a little bit more closely, you can see how hadrosaurs at different heights take up different parts of the amount of plants that are being consumed in a given area. And then you can see how the other dinosaurs compare to that as well. So the more a group takes along a certain axis, the more it is consuming compared to all the other dinosaurs. And so hadrosaurs seem to be responsible for consuming the greatest amount of plants above a certain height. And then ceratopsids are also one of our more greedy groups of dinosaurs before our ankylosaurs. Now, this doesn't really tell us much about what's going on at the small end. So what we're going to do is we're going to look at the really, really small stuff that's feeding only at about 1 meter off the ground. And if we zoom in, this is what we see. So hadrosaurs, which are feeding at about 1 meter above the ground, are responsible for consuming the greatest amount of plants at these heights. And based on growth curves, we can say that these individuals were only about 1 year old when they were eating the same vegetation as these smaller herbivores. And then it's only after they turn 2 or 3 that they become different, and they decide and they go on to feed at higher or greater feeding heights than the smaller groups of herbivores. So we're looking at something about this size, not much bigger than a horse or a very, very large dog. So where does this leave us in terms of what is going on during the Late Cretaceous? Well, previously we knew that the adults of the large herbivorous species were sharing resources with one another. And so we knew that that was how they were coexisting, but we didn't really know what was going on at the smaller size. So with what I did for my master's research, we started to fill in this picture a bit more, and we could say that these larger herbivores underwent dietary changes with growth. And so the young of these groups were very picky and selective about what they were eating. And then as they grew up, they expanded what they were eating, and they ate a lot more or a wider variety of different things. And that over the course of their evolutionary history, these groups evolved to occupy different roles in the ecosystem for the most part, save for juvenile hadrosaurids and ceratopsids compared to our smaller group of leptoceratopsids. So our juvenile hadrosaurids in particular, based on our browse profiles, seem to have not been fantastic with sharing their food, at least within the first year of their life, much like human babies. And that is all I have for you today, but I would definitely like to give a shout out to all the people that helped me with my research and my various funding resources, because without them, this would not have been possible. And I am happy to take any questions. And if you want to check out my research, it's all online.
Okay. Yeah, thanks, Taia. This is awesome. Yeah, never really thought about baby dinosaurs that way, like comparing them to the juvenile or to the small species. But yeah, like Taia said, thanks for the talk, and we're going to open up the question period. So if you have any questions, please type them into the chat box, and I will ask them to Taia, and hopefully she can answer some of them. So not seeing any yet. You did too good of a job to answer any questions I popped up with during the talk, because I saw the graph of the or the carnivorous dinosaur graph. I'm like, well, how does that relate to herbivorous dinosaurs? Because it makes sense, but you explaining the hadrosaurs grow up, and that makes sense because that'd be that middle chunk.
Yes. But up until my research, it was only a theory that had been done, investigated with math, and math is kind of not fun to look at.
Yeah, fair enough. Okay. Okay. The question did pop in from Max. Is ontogenetic niche partitioning seen in modern birds to any obvious extent?
So that is a fantastic question, and one that I often ask myself. And unfortunately, there's not a whole lot of research out there. There is like 1 or 2 studies that talk about it very briefly. So even though there is parental care offered by many bird species, there still seems to be some dietary change. And it's back to that function of the bigger you are, the bigger the things you can eat. So the smaller chicks, their parents come and they feed them smaller things so that they can actually get it down their gullet.
Okay. Yeah, that makes sense. Okay. While we're waiting for more, I may have missed it during your talk, but I'm just thinking, because hadrosaurs and like dinosaurs in general grew so rapidly, why would they be so picky as the very young juveniles?
So that's
wouldn't they want
fantastic.
like just fuel to fill the tank?
Well, the way this an ontogenetic niche shift works is that it helps alleviate competition between members of the same species. So you can get competition between members of different species that limit the amount of resources that you can take in. But you can also be limited by members of your own species. So by eating different things when you're smaller, you don't have to worry about the adults of your own family basically eating all your food. So you get rid of some of that competition.
Okay. Okay. Yeah, that makes sense. Okay, I'll give it another moment, but I'm not seeing any other questions. Your talk was just too good. Do I have any others? Let's see. Oh, it kind of makes sense why the hadrosaurs and ceratopsians would take up the biggest share of the food, because they're bigger. But did you see any separation between like the strategies or the amounts of food taken up by the different groups, like between lambeosaurians and hadrosaurians, or the centrosaurians or chasmosaurians?
Not so much, but unfortunately, trying to get sampling at the smaller sizes between groups is extremely difficult. So at this point, I'm extremely limited with what I can say as far as like overall. And that would be something that I would really like to look at in future, once we actually dig up more examples of these things. But unfortunately, it's just not out there yet.
Okay. So hear that, paleontologists, dig up more dinosaurs.
Exactly.
Okay, well, I've not seen any others, so I think we're going to end it for today. Thank you, everyone, for joining us. It was great to have a lot of people join us and listen to Taia's talk. This will be saving this to our YouTube channel so we can continue. Continue viewing it. But actually, a quick question did pop in. Given that small dinosaurs are so underrepresented in the fossil record, how do you account for preservation bias with small dinosaur species in your data?
So that is definitely a good question, especially regarding those browse profiles, which considered overall population size. So you can do this with some mathematical wizardry, where you can take like random sampling. We also can use things like pachycephalosaurodomes as an estimate of how frequently these individuals are being preserved, because they're more chunky and resistant to damage during preservation. So we can sort of use them as a benchmark to say whether or not we're actually picking things up as frequently as we would expect if we were to travel back in time. Another thing is that our juvenile hadrosaurs and ceratopsids are about the same size as these smaller groups. So they're going to be probably about as underrepresented as the rest of our smaller herbivorous groups. So they're going to be about the same chances of preservation as each other compared to the overall big herbivores.
Okay, hope that answered Tristan's question. Okay, but otherwise, like I was saying, thank you again for joining us, and stay tuned for our next virtual speaker series in March 31st, where we will have Steve Brissett talking about the rise and fall of the dinosaurs, which we're very excited to have him for that. So maybe Taia will join in and ask Steve a question.